Hello, and welcome to the Astroholic Explains. I'm Dr. Alfredo Carpinetti.
And I am producer Chris.
So, producer Chris, since this was your idea, what are we doing here?
So the idea for this podcast came about after a number of belligerent questions that I would badger you with. Eventually you had enough and said, no, stop it, let's just record these. We could share it with other people.
And here we are. I'm gonna be answering questions. I don't know what the questions are.
No, I'm just going to throw questions at you.
Hopefully I'll know the answer at least.
Well, I'm going to throw one question at you per episode, so hopefully it won't get too overwhelming and we'll just be able to chat about these things.
Sounds great.
Okay, should we dive in?
Let's jump in.
Okay, so today I've actually got quite a hefty question with possibly quite a bit of explaining to do, so I hope you've got your helpful hat on today. So today's question is about gravity and black holes.
Go on.
I can just imagine you're going to want to stop me through this entire question because I'm sure that so much of what I'm about to say is wrong. But black holes, they act in sort of 3D. Like the typical explanation of a black hole is when you have a sheet stretched out and you place on it a weight, and that pulls the sheet down. So it's a good representation of gravity or space-time being bent and pulled down towards this weight.
Okay, I'll stop you there because that usually is the representation of just gravity.
Okay.
Because
Well, that's
we need
good
to go with
because-
black hole. We need a step forward, but
Well, I think mostly what I'm going to go for today is gravity and mass. So if this is how mass works, it's black holes and form orbits around them, they form galaxies around them. A black hole has mass to form these orbits. Galaxies surely also have some form of mass. Well, what if multiple galaxies accumulate mass? Does the universe have like a collective mass? If that is the case, if all of these things weigh so heavily in 3 dimensions, why is the universe expanding, not collapsing in on itself? Why does everything appear to be moving away from everything else if mass and gravity can be factored?
Whoa. Okay.
I'm not even going to apologise. I'm quite pleased with that question.
No. It's a very, very interesting question.
Multi-part.
Multi-part indeed. As you're pretty much going full on on pretty much the biggest mysteries of astronomy.
Come at me, Einstein.
Yeah, come at you, Einstein. It's. I think it's a very, very strong start.
Good.
Let's start from the very beginning. In the words of Julie Andrews, is a very good place to start. So, why we do that representation about gravity is because from general relativity, we know that gravity changes the geometry of space-time. So it alters how space-time works around any object. Obviously, small objects like us and even the Earth create only a tiny, tiny effect. The bigger, the heavier the object, the bigger the effect. If an object is spinning, does this thing called frame dragging, because it's sort of twisting the space-time around it. And we measure frame dragging on even around Earth, I think. But it happens around. Obviously, the heavier the object, the easier it is to witness. So, if
That's why people don't have orbits. That is why people don't have orbits.
Yeah, like you are creating a gravitational effect. If you're moving, you're creating gravitational waves, but they're so tiny that they just don't matter.
Yeah.
I'm afraid. So,
Good.
the representation flat sheet, usually you see it with your big spherical weight represent a star, and then you have a smaller spherical weight that you send around
And it spins
and it
around.
spins
Yeah.
until a certain point falls in.
Yeah.
Why it falls in, that doesn't happen with gravity, is because the friction slows down the object, and so it loses energy, goes towards the center. This luckily doesn't happen with gravity. Anything that is orbiting is simply constantly falling onto the object in question, but missing. But it's great idea. It's a great concept. As it started by Newton, Newton wasn't just thinking, "Oh, the apple fell on my head. There must be something that is pulling it down." It's if you throw an apple, it will fall after, I don't know, you're very strong, I don't know, 10 meters. But could you be high enough on like a massive tower and you can throw the apple? Because if you're like 10 meters high and you throw the same apple, it might go much further because it also needs to come down as well as going away from you. So could you be on such a high tower that you could throw...
Sending an apple into orbit.
Yes, literally. But that was his idea. And at a certain point, he realized that, oh, if I can throw the apple around and it keep missing Earth, the force that pulls the apples down must be the same force that keeps the moon on orbit around the Earth.
Yeah.
So literally, the astronauts on the International Space Station are constantly falling on Earth. They just luckily keep missing. And it's the same idea
way
on
of looking at flying.
Yeah, but it's the same idea with why when you're sending a rocket into space, you don't need to just send them up. If you send them up, they're coming back down. You need to give them quite a high horizontal velocity so they can get into orbit.
Mm-hmm. And carry on going.
Yeah, so that was the first part. You have your standard sheet for the description, you're changing space-time. If you had a black hole, you would have to pull the center of that sheet
way down
to infinity.
Okay.
That's what we think is the singularity of the
3D.
black hole in 3D.
So it's not just being pulled downwards, it's being pulled in from the sides, from above, from
Yes.
below, in all
From
directions.
everywhere, yeah. And
Okay.
on top of that, you need to consider that the black hole is spinning, so you have the frame dragging and flattening. It's a lot of stuff, but we have good maths that help us do that.
It's this kind of idea that's made me then think, why is everything moving apart, not collapsing?
You are perfectly in line with the thoughts that went on until the late 1990s. So, first we started with Einstein had general relativity. General relativity is very complicated and there's a lot of solutions that don't represent the real universe. So you can put in stuff and you can create these weird and wonderful universes with weird mathematical properties and they don't match the real universe. Einstein put in his expectation for the real universe, found the solution, and then people started pointing out that his solution was not stable. It means that the solution would be changing. And the universe, as we know it, could not be static. The idea at the time was the universe has always been. Eventually, over time, people started putting in more evidence that the universe was expanding, and it all started as from a point, not a singularity, that was the Big Bang. Consider that the term Big Bang was actually scientists mocking the whole idea that it all started in a single point,
Yeah.
but it stuck. Afterwards, Rubin discovered with others that there was a lot more matter in the universe that we could see, the so-called dark matter. We still have no evidence that exists, but we have a lot of...
Just go by the idea that it does.
Yeah, and we have a lot of either our equations are wrong, which they could easily be, or there is this amount of dark matter that only interacts with gravity and not light. So at that point, they're like, oh, you know what? There is a lot more matter in the universe, even though the universe is, at the moment is expanding, simply because things started moving away from each other after the Big Bang. Eventually, the mass will pull everything back in, the big crunch.
Okay.
And that was to call as this is how the universe will end. And then we discovered that the universe is not only expanding, it's expanding at an accelerated rate. So
It's getting faster and faster?
yeah, so the estimation showed that the universe is not going to crunch back up. And the explanation for this accelerated expansion is what we call dark energy. A mysterious, because again, we don't know what it is, energy field that permeates all of space and time and pretty much push everything further apart. So we have this...
Gravity versus dark energy?
Yes, gravity versus dark energy, but dark energy seems that is going to win. We still have a lot of issue about it, but we know that measurement of what the expansion rate of the universe using the first light in the universe, the cosmic microwave background. First time that photons were finally free to move around the universe, about 380,000 years after the Big Bang. This light was observed by the ESA Planck satellite and made very, very accurate prediction for the expansion rate of the universe. And then we have other methods so that is from the very beginning of the universe, and tell us what the sort of history of this expansion rate should be now today, based on everything we know. And then we do measurements of the expansion rate using nearby and also not so nearby galaxies, and we get a different number. The two numbers have 9%. So the value that we measure nowadays is 9% higher than the value that we expect from the Big Bang.
Okay.
And there's only one chance in 100,000 that the truth is actually like a value in the middle, or that there is a mistake somewhere. We are pretty confident that there is something very wrong with our theory of the universe.
Yay!
And we don't know what it is.
Well, it's exciting.
It is absolutely exciting. It's fascinating, and it keeps us humble, because we know a lot about the universe, but the only certainty we have is how much we don't know. And it's a fantastic time. What a time to be alive, but it's very, very interesting to see how they're going to solve this conundrum. They're going to look up, they're going to obviously strengthen the measuring methods to make sure that everything is correct, but they're also going to expand searches for better understand dark energy, or how this effect is produced if dark energy, again, doesn't exist, because we haven't found evidence that dark energy exists. We're only seeing the effect of something that we call dark energy.
Okay, so understanding it correctly, it's basically the reason why everything is not falling in on itself is because of dark energy and acceleration.
Yeah, but things are also emotion. I know that gravity, the way we use about gravity is, things fall down. Mm-hmm. But also gravity lets things spin around. And I think this tension between our experience of gravity and gravity in space is something that people always ask me about the Sagittarius A star, the supermassive black holes at the center of the Milky Way, and they're just like, is it gonna sort of eat us? Although for material near a black hole, the black hole is a three-dimensional plug hole. If you're far away, you just orbit it. And so, if you don't have enough matter, things are not going to collapse. And one thing about dark matter is that dark matter is believed to be diffuse, so expand further out of what we see of a visible galaxy. And being diffuse sort of keep things in balance. So this is why the spiral galaxy have the spiral arms, because there is mass outside, mass inside, and it's keeping this sort of balance, and the structure of the galaxy remain quite stable. And so, yes, gravity can make you fall down and hold you back, but it can also make you spin and fly and go even further than you could ever thought.
I think that's quite a poetic way of putting it, but it fits. It seems to fit. But I think in that regards, I think the education system needs to overhaul the way it portrays gravity, in particular to younger students, because there's always that stereotypical image. When you first learn about gravity, it's up and down, it's things falling, and that's it. You don't learn about the spin until, I would guess, later on in a scientific education. Probably, but also it's very difficult to judge. This is a bias that we have before we even get into education, because I suppose it's what we see. Yes, it's our senses. You are our child, you trip and you fall down. You don't know that it's gravity, but you know. And spin before you fall. You don't know that it's gravity, but it is something that happens to you. Somebody say, oh, it's gravity, something is bringing you down. Mm-hmm. And we are the sum of our biases, so we just keep going, and we just need to tell people that gravity is not just falling down, and it's something that keeps us in orbit, it keeps us stable, and somehow also keep us safe. Okay, cool. Well, thank you for answering my stupid question of today. As always, it's my pleasure. Do you have any burning questions for the Astroholic? If so, send them in to me at Elucifer on Twitter, and I will spring it on him in an upcoming episode. See you next time!